recording and okay, so welcome everybody to slot 2 of the 4th day. So now it's Matt's turn with classifying combinatorial polynomials. Please.
Thank you. Are there any questions? Anything that came up since yesterday, or any questions about movie marathons or life, or okay. So here's what I want to do today. So I want to sort of talk a little bit about this more sort of general picture of semigroup algebras that appear in the world that we've lived in this week. And so, yeah, so I just threw this page on here from Monday, right? This was one of my examples where I sort of very briefly outlined one situation where you're interested in some sort of semigroup because it has some meaning, yeah, and so this is what I want to pick up again, yeah. I'll start with that, and then do the very general setting, and then go back to an example of something, yeah, that connects hopefully many things from this week. And that example will probably go on over to tomorrow. Okay, so so what did we have there? So so we had some lattice L, yeah, so that lives somewhere, and back then I said, you might as well assume that the lattice is z to the d, because every lattice is isomorphic to z to the d for some d, yeah. But now I'm actually interested, yeah, so this lattice is this was generated by some set that I called M, yeah. So let me remind you. So this means, any integer combination of things in M, yeah. So some lambda M times M things in M, and I'm generally interested in the case when M is capital M is finite. Yeah, and so this word length function that we were interested in, but again, this was sort of just an example. Was writing the minimal number of generators, so minimal number of generators. So these are the things in M, yeah, needed to write some element, yeah. And so now, now I want to mimic. I want to mimic what we did sort of in the thank you, the lambdas here. The lambdas, that's kind of important. So these lambdas are non-negative integers. Thank you. Yeah, and so I kind of like, I want to mimic my construction of homogenizing a polytope. Yeah. So so if you remember back then, I said, hey, let's take the convex hull of these generators. Yeah. So this is now something. This is a polytope living in R to the D, and I said back then, we're lucky we can sort of interpret things in terms of this polytope. Yeah? And I guess I want to take this now one step further. So okay, so what am I going to do is let's call this something P for polytope. And so I claim kind of like the analogous thing to this homogenization construction is that I consider another set of generators. Now, this is now a sort of one dimension higher. And so, as usual, I will write my generator as a matrix. And so now I'm really kind of well, okay. Let's introduce a notation. So what I want to write in this matrix are the integer points in P. So let's write I for integer points. So I look at all the integer points in P. So these are my generators and then some. So my generators are the extreme points. And so I homogenize now this set. So if you think back, at our picture, so that we had a polytope. I don't know. So here's a polytope, and that we call P. And the hom of P is the cone. Sort of, and you put this polytope at height 1 in another dimension, and so this green thing is hom of P. And so what I now do is something sort of like a discrete version of this. So what I now do is I look at the integer points in P. So these include the vertices, but there might be stuff in here. There might be some stuff on the boundary. And so now I generate a semigroup with that. And so from here I do same construction. And so what does this give me? So now just imagine you start adding, right? That's what I'm doing. You start adding those orange points. And so start adding those orange points is a little bit like adding the generators of my lattice, except that there's a little more going on now. So this the points in here. So the points in here are somehow so what I'm doing with this homogenization, I keep track, sort of the x, if this is the x0 coordinate. So the x0 coordinate here keeps track of how many generators I used. X0 coordinate. tells you exactly the number of generators. Yeah, and so now you can make sort of precise of what I said on Monday. So if you have a word length function, then I claim, so in this case, I claim the typical thing over here, this is just M and the origin. And so what you end up computing now here is not quite the word length function, but it's sort of like the less than or equal word length function because of the 0 in the middle. So so basically you're saying like, okay, I'm now looking at elements in my semigroup, but I'm allowing 0 as a summand, right? And so this computes a sort of a word length function, except that you're not saying I have exactly n generators, but you're saying I use at most n generators. But you can imagine, so once you have that function, you can compute the word length function from it. Okay. And so now I'm going back to what I said on Monday. So so this sometimes, you can see this in my picture, right? So this sometimes is the same as the integer points in Helm P, and sometimes not, correct? So now I'm in dimension d plus 1. Yeah. Well, so I guess in general I should say, this is part of it, correct? Yeah. So so I think of Helm P as a cone that's now maybe as a cone even generated in with real parameters from those orange points. And so, but inside that cone, there's sort of like a discrete version, where we generate integer combinations, non-negative integer combinations of these orange points. And so they sit inside the integer point structure of Helm P. If this is equal, if these two things are equal, then we say that P has the integer point decomposition property. IPD, IDP, integer decomposition property. Sorry. Yeah, so this is now for this now we don't need we don't need this top part. So so you start with a polytope, you look at all the integer points inside, and so now you're generating a semigroup with those points, one dimension higher. And that semigroup sits inside another semigroup, namely the semigroup of all integer points in Helm of P. If those two are the same, then we say that P has or is IDP, has the integer decomposition property. You can rephrase that, and sometimes you see this definition. You can rephrase this by saying like, so what does it have to do with P, right? That means that every integer point in k times p, right? So if you have a point in k times p, then m is the sum, it's the sum of k points, integer points in p. Points in p. Correct. This is the non-homogeneous way of saying this, and you can imagine this is kind of special. So a generic lattice polytope will not have this property. And so so the polytopes, the IDP polytopes, form a special class of lattice polytopes, and they often come from applications. So my word length application says, right, if I mean in a nutshell, if you're the polytope that you construct out of a word length problem has IDP, then your word length function is basically an Erhard polynomial. It's really the Erhard polynomial of a boundary of a polytope, but okay, I can compute it using Erhard polynomials. And if it's not, then somebody like me doesn't quite know what to do. If that polytope is not IDP, then we need other methods. Are there any questions about this?
Yes. So why are we putting exactly the integers point of P in our matrix M hat? We are putting I. I was wondering why I instead of just M.
That's a good question. And the reason is, at the end of the day, I want to have a semi-group structure. No, that's not true. No, you would still have a semi-group structure. You're absolutely correct. But I wouldn't have a polyhedral structure, I guess. So I mean, if you look at my picture, right? So if the orange points inside my polytope are not there, you can still construct a semigroup. Absolutely, that's just it's a semigroup by definition, right? If you start adding, the points, your generators. But I wouldn't have necessarily the geometry. It's a good question. And so I guess the really short answer is I want to use geometric methods.
I see, thanks.
In a sense, the next thing I want to do, in a sense, gets rid of that. And you'll see. So in some sense, what I'm showing you here is still something where I can draw pictures and where I can sort of describe it. But you'll see in a moment. I'm gonna more or less get rid of it. So you've seen polytopes with IDP, because I claim any polytope that has a unimodular triangulation has IDP. So there's sort of there's a hierarchy of polytopes. So polytopes who admit unimodular triangulations are a subset of the polytopes that have IDP. And in fact, you don't need quite a strong condition. That's one of the homework problems. is you only need a unimodular cover. Okay. And so this is the start of a sort of hierarchy of lattice polytopes. They sort of come in, you know, there's sort of lots of subset relations like this. And there are people, I've worked on this only very briefly, that there are people who sort of work on this hierarchy. They try to, you know, they have sort of classes of lattice polytopes that sit inside each other. Yeah, they're defined by properties like this, and then you can always ask, okay, this is a strict inclusion, so you have to find, let's say, a polytope that has IDP but no unimodular triangulation. It's not so easy actually to find such a polytope, but they do exist. And so there's lots of interesting questions there, and they have applications, algebraic geometry and in other fields. So they, you know, some of these notions come from other fields actually. But anyway, I sort of don't want to do that. I want to now really do a general setup. Yeah, so what's the general theme? So now, yeah, I mean, let me try to do this as general as possible, and then, yeah, look at special cases and then realize we've done this already. Yeah. So I have some semigroup. Yeah, so let's actually give this a name because it's going to appear all over the place. Yeah, so this is some finitely generated thing. I don't know. Let's still call this m hat. Doesn't matter. Yeah? But now my m hat is whatever. Yeah, and so the only thing I want this to be, you know, in some, you know, z to the, let's say, d plus 1. Yeah, because I still think the same way. Yeah, so this is a little bit, you know, taking this from the previous page. And so, okay, so now, you know, so this is, like I said, this is by definition a semigroup. And so the semigroup algebra, so many of you know this, you know, so whenever you have a semigroup with that are formed by integer vectors, yeah, so then you can look at them, you know, the monomials that correspond to these integer vectors. Yeah, so this is multivariate. So where m now is in the semigroup. Yeah, and so, you know, so you know, okay, let me write this first. Yeah. Yeah, so, you know, why these terms, right? So semigroup means, right, we can add because it's closed under addition, right? And algebra means we can, you know, we have a vector space structure. Well, you know, these are, so this, you know, the vector space is kind of like the space of all polynomials, but I have now, you know, polynomials with certain, actually Laurent polynomials, right? They're because m might have negative entries, so these are Laurent monomials with, you know, certain monomials allowing to appear. Yeah, but I can now multiply, and this comes from the semigroup, because if you take two monomials like this, you know, some z to the m1 times some z to the m2, what you're doing is you're adding the exponents, correct? And because your exponents come from a semigroup, that is another, you know, possible exponent vector. And so this thing is closed under you know, monomial multiplication. And so therefore also under Laurent polynomial multiplication. Yeah. Okay. And you've seen this. So out of this, we now, build a multivariate generating function. You've seen this in a special case. Yeah, and then often, you specialize. Yeah, so in the Erhard case, so this is called the grading, right? And we'll be more precise in a moment what this means. Yeah, so this you specialize this, for example. So here's one example. Yeah, so in the Erhard case, what we did is we said, hey, okay, I still want to sum over all. So this is still a vector, but I'm only keeping track. Maybe I should now do an x instead of a z, just so, because we have like several variables and single variables. I only keep track, let's say, of the first coordinate. So this is now on the left, you have a multivariate power formula Lorentz series. On the right, you have a single variable generating function. And then you can let's say if my m hat is like before and I only have like ones on top, then this records, let's say, some numbers, right? And sort of for the Erhard, this was actually our Erhard polynomial, but okay, these are some numbers. Yeah, sorry. This is now x. Yeah. Where the Cn just collect elements in the semigroup with the same m0 coordinate. Yeah. And so this, again, connects to the algebra. So this records certain dimensions of vector spaces that live in your algebra. So certain dimensions. Yeah, so this is what's going on here. And so now I want to, this is just to throw out throw the terms at you. And so now I want to apply this to sort of a very, very general problem. Okay, so sort of here's a very general sort of setup. Yeah. So you have some matrix of, let's say, a rank R matrix R by D with integer coordinates, and your goal is to enumerate, and I'm not sure what enumerate means. Yeah, so this could be counting, this could be listing, this could be form a generating function of some form. Yeah. Enumerate all the solutions with non-negative coordinates, integer coordinates, to the system phi times m equals 0. Yeah, so why? What's going on here? Right. So these form a semigroup, correct? Yeah. So if you have so this is a general linear Diophantine problem, correct? So so if you have a matrix phi and you want to find all things in the kernel there, or even over Z, that's not a problem. But so the magic here is that I'm only allowing so this is, this makes this problem hard. Yeah? So I'm only allowing non-negative entries. Yeah? And so now, I don't have a group structure anymore, but I have a semi-group structure. If you give me an element with non-negative coordinates in the kernel of phi, and you give me another one in the kernel of phi, I can add them and I'm still in the kernel. Well, I'm still in the kernel and I'm still non-negative. That's the point. Yeah. So, if you did this in linear algebra, or maybe, in a course on modules or something like this, yeah, then you did this just over Z, and the methods for this are centuries old, correct? Yeah, but in combinatorics, you often only allow non-negative solutions, and so now in algebraic terms, you are operating in a semigroup. Yeah. And so this is sort of like the most general setting I want to be in, and I'll stop for questions in a moment, but I want you to realize that we've done this, okay? We've done this with our polytopes, yeah. So if you give me a polytope, yeah. So let's say r to the d, and it's given by a system of linear inequalities. Then, well, I want to construct a semigroup first. Yeah. So, so the first thing is I'm gonna make inequalities into equalities. Yeah, by introducing slack variables. Yeah. So this is now a new A, right? So new matrix A, but okay, I can. Yeah. So. Yeah. So. And a new D, I guess. And so you need more variables now, but yeah, so now I can, by introducing slack variables and I guess some translations of my polytope, and if you're only interested in integer points, you can do integer translation. I can assume, so I should say that, so, move, translation, and slack variables, you can assume that P looks like this. And okay, and so where is the semigroup? Well, then, so now, my hom, right? So my hom is, so now I'm going up one more dimension, right? So now I'm in D+1 dimensional space. And, nice, so my additional variable is non-negative, correct? Yeah, and so, yeah, so now we're doing what we did on Tuesday. So I throw in an x0 as a scalar in front of my vector b. Yeah. And so I guess my my matrix here, my matrix phi is yeah, so I should move this vector b to the other side. So I have a negative b and then my matrix A. Mm-hmm. And so then my semigroup is precisely the integer points in hom P. And sorry, I guess I'm assuming that my polytope here is rational, right? So yeah, so I want to have, I want A and B to have integer entries. Yeah, and so, not just that, so my semigroup is that, but the elements in here, so if I have an element, let's call it T, M, right? So this was our setup on Tuesday, right? So if I have an element t comma m, this corresponds to an integer point, right? M in t times p, right? So, yeah. And so, yeah, so I hope this is convincing that this thing here is more general than what we did on Tuesday. Okay. This is a good time for questions. I'm talking too long today.
So I'm a little confused by that greater than or equal to 0. Like, is this the usual toric setting, or am I missing something? I mean, is something different?
So the toric setting really comes from a polytope. Yeah. Yeah, so the toric setting really comes from a polytope. So what I'm doing here is, in some sense, more general. Yeah, in some sense.
I have a question. Would it be possible to draw a picture or to like show on the previous picture like how this would look?
Oh, what look?
Like the process, I guess the algorithm that you just outlined.
So, I mean, do you mean in my example, Marielle?
Yeah.
I'm hesitating.
It's okay if it's
no.
too like.
I'll tell you why I'm hesitating. I'm hesitating is because I'm precisely stepping away from the pictures. I'm precisely stepping away from the geometry for a moment. Okay. And the upshot of today, the message that I want to send today is sometimes you want to do that even though you want to do geometry. That's the message today. Yeah. So the pictures behind. Okay. The picture behind this is what you saw on Tuesday. I have a polytope and I take the hom of it. So I take this cone, and in this philosophy, you can say like, okay, I wanted to take the cone because I wanted to construct a semigroup. Yeah, cones are nice because they, if you take two things in a cone and add them, you stay within the cone. That's more or less the definition of a cone. And so that's the same definition of a semigroup. Yeah. And so in hindsight, like from this perspective, that's why you're doing the hom. Is if you have a polytope by itself, there is no algebraic structure a priori. But as soon as I go one dimension higher and do this coning thing, I have a semigroup, and then I can play this game. Yeah. This thing, in some sense, doesn't have a picture. This is a combinatorics trick where you say, okay, yeah, you convert an inequality into an equality by adding more variables. And so you know, so again, up here, I sort of think, I think precisely not geometric, which is a funny thing for me to say, because almost everything I do, it has sort of a geometric meaning to it. Yeah. Yeah. We'll yeah. Maybe this is not satisfying, but we'll draw pictures soon enough. Yeah. We'll draw pictures. But again, so the point, and you will see this in the second half, the point is sometimes you want to think about this, yeah, so you actually want to draw pictures, yeah, and sometimes you just want to think about this sort of abstract construction of a semigroup. There's still some integers floating around, and so, you know, I can still, you know, make these connections, but I want to ask things like, if you give me such a matrix, yeah, here's, I just defined a semigroup, you know, how can you generate a semigroup? Yeah, so this again connects to the some of the other lectures that you've seen with Martina and Uwe and Dixon's lemma and so on. Yeah, so this is sort of what's behind there. Yeah? And so, yeah, so in the case where the semigroup comes from a polytope, we can sort of say what the generators are. But sometimes you actually want to step away from this and just think about abstractly and realize how you can generate a semigroup.
Thank you.
I'm still thinking about Alessia's question about the toric picture here.
We can also discuss that later if you want to go on.
Maybe, yeah.
It was just a
Maybe
curiosity.
we should do that. Yeah, maybe I shouldn't think on the spot. It's not always healthy. Yeah, there's probably a general toric picture here. Yeah, there's probably a general toric picture here. I don't really do toric methods. So I don't, this is not second nature to me. So yeah, maybe we'll discuss later. Okay, shall we take a 10-minute coffee break?
Yeah, so it's 5:45. So we resume at, sorry, well, 4:45 whatever. So we resume at 5:02.
Okay. Any questions came up over coffee? So I didn't drink coffee, but I thought a little bit more about Alessia's idea, and I think sort of the toric construction is of course related to all of this, but it's something slightly different. So there, you start with an integer matrix that you think of as your point configuration, and then compute actually the kernel of this matrix, and you make a binomial ideal out of that kernel. So honest, the integer kernel. Yeah. So so in some sense, that's sort of like a dual. You're somehow working in the. It's sort of a dual approach to what I'm doing here. What I'm doing here is sort of more direct. Yeah, it's all related. It's all related, but yeah, it's yeah, and you can compute sort of many things through sort of dual ways. Yeah, but in some sense, what I'm doing here is more direct than computing things through toric ideals and so on. Yeah, that was
Thanks.
Just an afterthought. So okay, So let's give the semigroup a name. Okay, so S. S now means this setup, and so maybe actually let me keep this. Let me keep the setup up on top. Tell you sort of the theorem for this. So it's another theorem of Stanley. This is in 1973. So he developed sort of a setup, for computing this sort of multivariate generating function for semigroups given by such a system. And he proved in very general terms, so this evaluates to a rational function in several variables. He tells you what to expect in the denominator. So in the denominator, you have a product of terms 1 minus some monomials, where m ranges through a certain set, depending on the semigroup, that he calls completely fundamental solutions, or completely fundamental elements. Things in here have the property. If you think about a semigroup, so this is kind of like so a completely fundamental element in the semigroup is one that can't be decomposed any further into as a sum. But you can do one better. So that would be, I guess, a fundamental element in a semigroup. You can do one better. So this is an element such that if you want to take a multiple, k times m, integer multiple, and you write this as the sum of two elements in S. So these here are just some elements in S. Then the only way to do this is sort of in a trivial way. So the only way is that x is some multiple of m, and then y is the complementary multiple of m. So if we think back to our so here comes a picture, Marielle. So if you think back to our the homogenization of a polytope, then you should think of the vertices as the polytope. So a vertex gives rise to a generator. And a generator you cannot decompose as a sum of other things in my cone. So if you have something other than a generator, that'll be the sum of two generators. So in my example, so in HOM, of P, and these are the generators of the cone. So generators of the cone, and they correspond to vertices of P. yeah, so so this is what to expect. Yeah. And so, this is a very general setting, very general theorem. Yes, I'm computing this formal power series. So the typical thing now is you want to apply this. And the typical thing is now you're computing Hilbert series. Yeah. So, so in some sense, so some people call this thing a multivariate Hilbert series. Yeah, multivariate Hilbert series, but the typical thing that you want to do is you want to look at a grading. Yeah, so let's talk about this next. So we're now going to fix a grading. So I should tell you what this is. So in this setting, you can think of a grading just as an integer vector. So let me assume, so my semigroup lives in Z to the D. Yeah, so this is an integer vector. It's really in the dual space, but who's counting? Yeah. And you want to have a condition, and that is if you look at if you look at all vectors, all elements in your semigroup that give you a dot product 0 with your vector A, you want this to be only the origin. So in my example, you have some in my favorite applications of this, you have some hum of some polytope, so you have some cone, and so in terms of your grading, what you should think about is a hyperplane with a normal vector A. Yeah. And so what we're saying here is I want this hyperplane to be a certificate for the vertex of the cone, the apex of the cone. Yeah. Okay, and then so once we have this, we can compute the Hilbert function with respect to this grading. Yeah, so maybe let's call this H sub A. And so this is now the number of elements in your semigroup for which this dot product is equal to n. Yeah, and so the picture that you should have in terms of the hum of a polytope. Yeah, so now you take your hyperplane defined by A and you move it into the cone, and at each step, for each n, you count how many points there are. Yeah, so if I want to do this for the Ehrhart series, then my A is the beautiful vector 1, 0, 0, 0. Then I have a horizontal hyperplane, and I just go straight up. But you can do this for other hyperplanes, and so we talked about this a little bit on Tuesday. So that's what makes an Ehrhart polynomial is a special case of a Hilbert function. And then for this, you can compute the Hilbert series, which is the generating function. Yeah, so maybe, I don't know if we need that, but let's give the name. So capital A. So this is the generating function now of this Yeah, so this is a single variable generating function. And so this is a special evaluation. Yeah, so yeah, of what we did before. Yeah, so yeah, just like what we did on Tuesday, the Erhard series is a special evaluation of the integer point transform. Yeah, so this is my multivariate Hilbert series, right, which I didn't give a name, so I have to write it down. Yeah. Yeah, so remember these are now vectors here. Yeah, and so I evaluate this at c equals z to the a1. So this is a single variable. Maybe I shouldn't call them z. Let's call this x. X. X to a1, x to a2, and so on. So, what does this mean now for this theorem, right? So, yeah, so what happens now when you specialize, then we get a rational function with denominator some product of 1 minus a single variable to some power. You know? And so we can sort of like we can sort of, you know, so this is, I guess this is a corollary, right? And so corollary now says that this Hilbert series is a rational function with a denominator one minus x to some power p, you know, all to some power q. Right, so I have different factors of 1 minus x to some power, and so, you know, you can multiply top and bottom to get it sort of to this sort of like this generic form. Yeah, and so you can convince yourself that this q has to be d plus 1. Okay. And so now we're very close to the Erhard setting, right? So in the Erhard setting, you know, this becomes the Erhard series. Yeah, and so we had the rational function, you know, with an h star on top, divided by 1 minus x to the d plus 1. And so I guess, you know, here q is equal to 1. Yeah. And so, there's various reasons why I wanted to show you this, but one reason is yeah, sort of in this very general setting, yeah, of you give me some crazy matrix, you form this very, very general semigroup. Yeah. Then, you know, at the end of the day, you know, and you give me your grading that you want. Yeah. At the end of the day, these counting functions, they look not too far away from, you know, Erhard polynomials. Or as a generating function, not too far away from Erhard series. So that's one message. And the other message is you now have sort of two ways of thinking about that. And you will see an application of this tomorrow. Yeah. So the kind of situations that I'm thinking about now is I have some problem. Okay, we'll do an application back in graph theory tomorrow. Yeah, I have some problem. that I translate into sort of an Erhard problem. And so, that means I have to compute Erhard polynomials or Erhard series or something like this. But I don't quite know the structure of the polytope behind it, or the polytopes, I should say. It's going to be a family of polytopes, and I don't quite know the structure of the polytopes. I know that they're polytopes. I can't quite write them down. And so now I'm in a situation where you might want to think about computing this set straight up from the combinatorial problem. So I have some combinatorial situation. I move it into geometry and realize, okay, I can compute Erhard polynomials from some polytopes. Except I can't compute the polytopes. And then I say, wait a minute, let me go back into relational setting and think about what completely fundamental solutions should look like there. And so that's what I meant when Marielle asked me this picture question earlier. So sometimes I'm in situations where I sort of like I switch between two worlds back and forth. Sometimes this is useful. Anyway, you'll see this tomorrow. I wanted to tell you something else about this, but before we go on, I want to stop for questions. Anything that's not clear or where you want to hear more?
I think I've lost a step somewhere because I didn't quite catch why we have a single P in the corollary. Like I thought that the grading was a generic, I was expecting to get several pieces in the denominator.
Sorry, can you say it again?
Yeah, so in the corollary, you have that the Hilbert series HA, so the one that depends on the grading A, has a denominator which is 1 minus x to the p at a certain power q. So there is just one single p, and I was expecting like something like a product of several 1 minus x to the a1 or something like that.
Yes,
so
yes.
Why does that happen?
No, you're absolutely right. So your denominator looks like x to the, whatever, p1 and times 1 minus x to the p2 and so on. Yeah, but now I can take numerator and denominator and multiply it by some finite geometric series to get it into this sort of generic form.
Okay.
Yeah. You take my p there would be the LCM of p1, p2, and so on. Yeah. So my rational function might be not at all in lowest terms. But I'm using the least ink to write down the denominator. And there's a reason why I wanted to write it like this, is because I wanted to make the connection to what we saw with Erhard series. Yeah. But Alessio, I think it was Alessio is quite right. Yeah. So so in the Erhard case, this is more or less always in lowest terms, at least if D is the dimension of your polytope. Yeah. And in this sort of more general settings for Hilbert series, there is often your rational function is not written in lowest terms. And it's interesting sometimes to write it in lowest terms, to factor out as much as you can between numerator and denominator. And sometimes it's interesting to write it in a form that's actually like this, where you want to compactly sort of see just, this power d plus 1 and like this p that comes from all of your factors. Oh, okay. So this gives me a chance to talk about quasi-polynomials because this is what happens here. Yeah, so if I have some generating function, so let's say it was the Hilbert series of something. Yeah, so I have some generating function that looks like some numerator. Let me just call this h over 1 minus z to the p to the d plus 1. So, yeah, and so this is an honest rational function. So I want that the degree of the numerator is less than the degree in the denominator. And so again, so this is, so this is a generating function, right, of something. And in fact, we call this something, the Hilbert function, z to the n, right? And I claim, so I claim this thing here is, this is in some sense by definition a quasi-polynomial. So, what does that mean? So this means my, so my favorite definition of a quasi-polynomial is it's sort of like a piecewise defined function where your pieces, let's just call them P0. There's too many P's floating around, so I shouldn't call them P. Let's call them Q for quasi. So Q1 down to Q P minus 1. So there's P pieces depending on what n is modulo P. So that P is this P. So here's 1 down to P minus 1. And these things are polynomials. Yeah, so they're called the constituents. It's a good name, constituents of the quasi-polynomial. Yeah, so in other words, a quasi-polynomial is kind of like it's kind of like a list of polynomials. So I really think of this quasi-polynomial as defined for n for integers. Yeah, and so it's like a list of polynomials that you cycle through as n goes through the integers. And so if p is 0, if p is 1, then and a quasi-polynomial is just a polynomial. Yeah, and so, so what I'm writing down here is something that is, I guess, maybe should be another exercise. Yeah, so I claim a quasi-polynomial is precisely a function that you get out of a generating function like this. Yeah, so it comes from a rational generating function whose denominator, is not anymore of the form 1 minus z to some power, but 1 minus z to the power to some power. And so, so again, I'm not going to prove this, but let me do an example. Yeah, so let's say my quasi-polynomial, I'm going to run out of letters, so let's just use n. So one quasi-polynomial is, one example is something like this. So we have my n looks like it's coming from a polynomial, and then I have a constant term that switches between plus and minus 1. And so, so this quasi-polynomial has two constituents. One is n plus 1, and the other one is n minus 1. And I'm running through them, depending on whether n is even or odd. And so just to see this in action, so let's compute the generating function of this quasi-polynomial. So I imagine it's some Hilbert function. And so let's do it. So what do we have to do? So there's sort of, well, there's my n part. Okay, so that's good, right? And then I have this plus minus 1 depending on the parity of n, right? So if n is even, I get a plus 1, and if it's odd, I get a minus 1. And so now you can start computing, and you can see sort of where these extra powers come from. So this is what? This is like z over 1 minus z squared. And then this is a geometric series in the variable z squared. And this is another one, but I have an extra z up on top. Yeah, and so you can see now, so this is in the form that Alessio was mentioning earlier. Yeah? So maybe initially I want to write this over denominator 1 minus z squared times an extra 1 minus z, right? Sorry, I need a 1 minus z squared, so maybe I should make this a 1 plus z. Yeah. And I get some denominator, and if I computed this correctly, so don't quote me here. If I compute this correctly, this is a 2z squared minus z plus 1. But I could also, expand the denominator and numerator and make this a 1 minus z squared. And I believe this is, so again, I computed this earlier. This is a 2z cubed plus c squared plus 1. Yeah, so this is typical. What happens with quasi-polynomials, you might have different forms of the rational function. Are there any questions about this? Okay, so let me make some remarks. Okay, where does this p come from, right? So, okay, maybe I should do a setup. Yeah, so we have some quasi-polynomial. Yeah, so we have some quasi-polynomial that, let's say, is a Hilbert function. Yeah, it has degree d and period p. Yeah, so. Yeah, so by this I mean, yeah, so the generating function, yeah, so the generating function, yeah, think about the Hilbert series is of the form, something over 1 minus z to the p all to the power d plus 1. Yeah. I mean, degree is the right term here, is because these polynomials over here will have degree less than or equal to d, and at least one of them has to have degree d, I claim. And the period p just means, this is how you cycle. So these are good names. And okay, so come my remarks. So number one is like, okay, where does P come from, right? So so let's go back. Okay, P comes from here, right? There it is. Which really means it comes from here, right? It comes from here after specialization, right? So this was multivariate, yeah. So remember, these things here are still multivariate generating functions, and after specialization, and we consider read off, the period of your quasi-polynomial. Yeah, and so I know P if I know the completely fundamental solutions of my semigroup. And this goes a little bit with my remark that you sort of sometimes want to go back and forth. Yeah? So this comes from here. But right. Yeah, so in once you compute the rational function, right? Once you specialize and compute this function, things might cancel, yeah, and things might cancel so much that whatever P you expected from the completely fundamental solutions, actually at the end of the day doesn't end up appearing in your generating function. Yeah, so maybe I shouldn't say but. Yeah, so watch out for cancellation. Yeah, so for polynomials, this can't happen. Yeah, for polynomials, I claim 1 minus z will never be a factor in the numerator. Yeah, but for quasi-polynomials, this very much can happen, and there are some famous examples where this happens. There are some people who study this phenomenon, precisely this phenomenon. Yeah? When does this called period collapse? When do we expect a certain period from your semigroup setup, but your generating function ends up with a smaller period. Okay, so this is one remark. The next remark is, okay, what's the computational complexity here? So at a very, very basic level, so if you have a polynomial, so if you have a polynomial of degree d, right? So degree d, you need d plus 1 pieces of data, correct? For example, you need to know the coefficients, or you need to know the roots of the polynomial plus 1 coefficient. Yeah, so you need d plus 1 things, and if they're not like too close together, yeah, then they determine your polynomial. Okay, and so now for a quasi-polynomial, so again I have degree d and period p. So for a quasi-polynomial, well, we have p polynomials of degree up to d. Yeah, so we need p times d plus 1 pieces of data. So in practice, if you want to compute and you can get your p down, that would be good. So so in practice, cancellation could be really good. You know, so often the degree is given to you because this is like some dimension of something, yeah. And the period we don't know, you know? And if the period is unknown, you're really in trouble. You know, then you don't, you know, it's a finite it's a finite problem, but you don't know, you know, you don't know the complexity. And if the period is known, that you know the complexity, and if the period can be made smaller, then the complexity is smaller. You know? It's a good thing. And the last comment is, okay, you know, what happens with in the Erhard case? Yeah, so where does this appear in the Erhard case? You know, so this actually applies when you have a rational polytope. Yeah, so when P is not a lattice polytope, when the vertices yeah, so this means, you know, vertices are now in with entries in Q. Yeah. So you know, when we started the setup, you know, we had some linear system, right, with integer coordinates. And where's my polytope? Yeah, so here's here's my polytope, and I'm not saying anywhere that I'm not saying anything about the vertices. You know? The only thing is my linear constraints have to have rational coordinates. Yeah? And you can translate this into saying that the vertices have to have rational coordinates as well. Yeah? So this applies actually, you know, this setup actually applies to something more general than what you saw on Tuesday. And so there's a whole theory here of you know, Erhard quasi-polynomials. You know? You can convince yourself that the period here, or sort of like the expected period, is what's called the denominator of the polytope. It's a good name. And so this is the LCM of all denominators that appear in coordinates on it for all vertices. You know, so look at all your vertices of the polytope. They're now rational numbers. Yeah. So take all these rational numbers, look at the denominators, take the LCM of the denominators. That's the denominator of a P. Yeah. It's the minimal multiple, integer multiple, that you need to multiply P with, dilate P to get an integer polytope. That is a priori the period that you should expect for your quasi-polynomial. But same comment, yeah. Sometimes you can have cancellation. Yeah, so cancellation means that your period will be a divisor of this denominator. If you do Erhard counting, yeah, for rational polytopes, you will get a quasi-polynomial. And the degree of this quasi-polynomial will be dimension of the polytope. And the denominator will divide the denominator of the polytope. So yeah, so now we're back. Now we're back in geometry. Yeah. And same thing applies here, right? So if I give you now a concrete polytope, I can compute the denominator, and then I know the complexity of what I have to compute. So, you know, that's good. At least it's good if the complexity is not too big. But so what I'm going to do tomorrow is I want to show you, you know, sort of one application where all of these things go you know, come together. And it's a situation where, you know, I guarantee from the get-go that I have rational polytopes. but I don't necessarily know all the pieces. And so that means I can guarantee you there's a quasi-polynomial somewhere, you know. But so the magic now is to compute enough of that so that you know the period of this quasi-polynomial. And this is where I'm going to go back and forth a little bit. You know, so I can think of sort of the polytopes, or I can think of the semigroup, you know, generated by those completely fundamental elements. And yeah, sometimes it's good to think about one, and sometimes it's good to think about the other. Okay, we've got 2 minutes left. Are there any questions?
Maybe we can stop the recording before, unless you want to add something to the lecture, Matt.
No, please.
Okay, then let's stop it.